Hello, welcome friends to our AI course presented by Nehemiah STEM Research. My name is Muheli Donald Hastings, and today I'm going to be taking you through an introduction to computer science. So today in this session we're going to understand what computer science is, look at or define some software development basics, data structures and algorithms. Just a few networks and cybersecurity essentials and artificial intelligence overview. So we are just going to cover a brief introduction, and then from then on we'll look at the deep dive into all of these topics. So before we get started, here is our 8-month course outline for that very intelligent student. So as you can see, week 1 and 2 is computer science fundamentals. So this is day 1, introduction to computer science. And then from week 3 and 4, there's Python and LinkedIn profile. Weeks 5 and 6, data structures and algorithms, and then it goes on and on. So what is computer science? Computer science is the study of computers, algorithms, and systems used to process and store information. In that definition, there are 4 key areas that we need to understand. That is software development, data structures and algorithms, networks and cybersecurity, and artificial intelligence. So an important note to take is that computer science impacts every field from healthcare to entertainment to business. So it's a universal universal industry entity. Let me say it like that. Okay. I just want to make sure you are able to see what I am presenting. Okay, so I was in a full screen, so I'll stick to the slides instead of presentation mode. Okay, so yeah, as I was saying, computer science is the study of computers, algorithms, and systems used to process and store information. The four key areas of computer science are software development, data structures and algorithms, networks and cybersecurity, and then artificial intelligence. And I was saying that an important note to take is that computer science impacts every field, from healthcare to entertainment to business. So computer science, you'll find computer science in hospitals or pharmacies, basically the whole healthcare sector. In entertainment, you can see what it's doing with like social media and so much and so on and so forth. In business, you have CRMs, ERPs, and etc. So these are the key concepts in computer science. We have algorithms. Algorithms are step-by-step procedures used to solve problems. And then data structures. These are ways of organizing and storing data. We have arrays, we have trees, and then they're like graphs. And then software engineering, the design, development, and maintenance of software applications. And then machine learning, which is a branch of AI that focuses on algorithms that allow computers to learn from data. So, a brief introduction to artificial intelligence, or AI. So, artificial intelligence refers to the simulation of human intelligence in machines designed to think, learn, and problem solve like humans. The categories of AI, there's what we call narrow AI or weak AI. These are the AI systems designed to perform a specific task. Those are the earlier models you've seen from like Siri and the Google Assistant. And then general AI or strong AI are the AI systems with the ability to perform any intellectual task that a human can do. Currently, theoretical. So the role of computer science in AI is number one, algorithm design. So AI relies on computer science to develop algorithms that enable machines to process information and make decisions. And then the other role of computer science in AI is data processing, where computer science principles are used to manage large data sets and ensure that AI systems have access to high quality data. The third role of computer science in in AI is machine learning. This is the significant area where computer science intersects with AI, particularly in designing and optimizing learning algorithms. Then we have neural networks. This is a branch of AI inspired by the human brain, implemented using computer science principles to train models for tasks like image recognition and natural language processing. And then we're going to look at how computer science supports AI applications. One of the ways is, of course, programming languages. Then we have big data, then we have cloud computing, and then performance optimization. So under programming languages, Python, yes, sorry, just doing some things there. So yeah, we have Python, we have R, and Java are the commonly used programming languages in AI development. Yeah, when I put full screen, it doesn't, it stays like that. Sorry, yeah, so I was saying Python, R, and Java are the commonly used programming languages in AI development. And then under big data, so computer science enables the processing of vast amounts of data that AI algorithms need to improve accuracy and predictions. Of course, the data, we'll learn later that data is used for like training the algorithms to train so that it can improve accuracy and predictions. And then cloud computing. Computer science technologies enable the storage and computing power necessary for AI applications through cloud services. And then define the performance optimization. Computer science focuses on optimizing AI models for speed, accuracy, and scalability. So performance optimization means like, let's say when you're scaling, it means you're reducing the size of the model. Yeah. Let's say so that it doesn't lag when it's processing data. And then of course for accuracy. So real-world AI applications. Where do we apply AI in our world today? We have healthcare, we have finance, we have autonomous vehicles, and then natural language processing. In healthcare, AI is used for diagnostics, predictive modeling, and personalized medicine. I'll give an example. Nehemiah STEM Research has a skin dermatologist model where, let's say, the AI predicts or diagnoses skin conditions. So how it works is it takes, or the user uploads a picture of the affected area of the skin, and then the model will analyze that picture of the skin condition and then give a diagnosis based on the training data it has taken, and then it will also give an accuracy score. So that's just an example. And then in finance, AI algorithms power fraud detection, and then they're also used in investment strategies and risk management. And then of course we could look at the crypto networks, and and all that. So it's a large, there's so much it can do. And then autonomous vehicles, AI systems enable self-driving cars to process sensory data and make decisions. And then the natural language processing, this is the common one that I guess people know most. So AI helps in understanding, interpreting, and generating human language. For example, chatbots and language translation. So an example is like ChatGPT. That's basically natural language processing, where like you can talk to it like a human being and it will understand what you're saying. So could look at the future challenges in AI and computer science. So there are ethical issues, of course. There's concerns about privacy, fairness, and potential biases in AI systems. I guess maybe like in healthcare. Yeah, that's the one I can think of where they're mostly, of course, also as well finance. And then another challenge is data quality. AI systems depend on high quality, unbiased data to make accurate predictions. And then computational power. Training AI models requires significant computing resources. So yeah, that's one of the big challenges in AI and computer science. Then interpretable AI. Making AI decisions understandable to humans is an ongoing challenge. Basically explaining how the AI came to those decisions to people. So the future of AI and computer science, we have advancements in deep learning. The future of AI is likely to see more sophisticated deep learning models, enabling machines to process data in ways that are closer to human cognition. And then AI in everyday life. AI is set to become even more integrated into daily life, from personalized services to smarter homes. Yeah, this is the future of AI. We will be seeing it integrated into more and more systems. Ethics and regulation. As AI technology evolves, so will the frameworks for ensuring ethical use and fairness. So, a conclusion for artificial intelligence introduction. In summary, computer science forms the backbone of AI, providing the algorithms, the data handling, and the computing infrastructure necessary for the development of intelligent systems. And the impact of AI, the applications of AI are vast, revolutionizing industries and shaping the future of technology. The final thought, as AI continues to evolve, computer science will remain at the forefront, enabling more powerful, efficient, and intelligent systems. So you're in the right place with computer science, because you'll be basically involved in everything. So, an introduction to algorithms and problem-solving techniques. We'll define an algorithm again. An algorithm is a step-by-step procedure or formula for solving a problem. The characteristics of algorithms. Number one, they are clear and unambiguous. Every step is precisely defined. Finiteness. An algorithm must terminate after a finite number of steps. Then input and output. The algorithm takes inputs and produces outputs. And then effectiveness. The steps should be basic enough to be carried out. Why algorithms are important? 1. Efficiency. 2. Optimization. And then thirdly, automation. In efficiency, algorithms help solve problems in the most efficient way possible. In optimization, through algorithms, we can improve speed, memory usage, and other resources. And then in automation, algorithms are the foundation of automation in software and systems. Then a few types of algorithms. We have sorting algorithms. These organize data in a specific order. For example, bubble sort. quick sort and merge sort. Then we have searching algorithms. These are used to find elements in data structures, for example, a linear search or binary search. And then we have what we call greedy algorithms. Excuse me. These make the locally optimal choice at each step. For example, Huffman coding. And dynamic programming. So these break down problems into smaller sub-problems. For example, Fibonacci and the knapsack problem. Then divide and conquer algorithms. These break the problem into smaller sub-problems, solve them, and then combine solutions. For example, merge, sort. Then backtracking. These algorithms explore all possibilities to find a solution. For example, like solving a maze. Problem solving techniques. Step 1, these are the problem solving techniques of algorithms. The first step is it understands the problem. So it identifies the inputs, outputs, and constraints, and then breaks the problem down into smaller parts if necessary. Step 2, it plans the solution, so determine the algorithm or approach that fits the problem, and then choose between different techniques, for example, divide and conquer, and then dynamic programming. The third step is implement the solution, convert the plan into code, test the solution for correctness, and step 4, optimize the solution, improve performance if necessary, that is time and space complexity, and then check for edge cases and validate the results. Algorithm design strategies. Brute force. Try all possible solutions until the correct one is found. For example, checking all passwords. Divide and conquer. Divide the problem into smaller, manageable sub-problems. Greedy approach. Make the best local decision at each step. Dynamic programming. Solve problems by breaking them down into simpler, overlapping sub-problems. And then backtracking. Try solutions and backtrack if the solution is not valid. The time and space complexity. So the big O notation, this describes the upper bound of an algorithm's time or space complexity. We have O1, that's constant time, for example, accessing an array element, or N, that's a linear time, finding an element in an unsorted list, and or N squared, that's the quadratic time. Then or logarithm n, it's the logarithmic time, for example, the binary search. Then space complexity, this measures the amount of memory an algorithm uses relative to the input size. So we always aim for low space complexity to assure efficiency. So an example of sorting algorithms, bubble sort. Let's compare the adjacent elements and sort them if they are in the wrong order repeatedly, and then repeatedly pass through the list. Time complexity or n squared, space complexity or 1, merge sort. Divide the list into halves, recursively sort them and merge them back together. Then the time complexity or n of logarithm n, space complexity of n, quick sort. You select a pivot, partition the array and recursively sort the partitions. Time complexity or n of logarithm n times the average or n squared, and then the worst case, and the space complexity or logarithm n with the average. Some problem solving examples. For example, find the largest element in an array. With the brute force approach, you loop through the array to find the largest element. And then time complexity is of n. Example 2, Fibonacci sequence. Recursive approach, solve by defining the function recursively. Dynamic programming approach, store the previously computed Fibonacci numbers to avoid recomputation. And then time complexity with the recursive approach, O to the power of n, and then time complexity of n. So here are some of the common pitfalls in problem solving. So 1, not breaking down the problem. So failing to divide the problem into manageable sub-problems can lead to confusion. Ignoring edge cases, like let's say if you overlook special cases like empty lists, null values or negative numbers. Overcomplicating the solution. Sometimes a simple approach can be the most efficient. And inefficient algorithms, choose an algorithm that balances both time and space complexity. In the real-world applications of algorithms, we have search engines. So search engines use algorithms to rank pages, retrieve results, and analyze keywords. Social networks, algorithms help recommend friends, posts, and advertisements. Cryptography, algorithms are used to encrypt and decrypt sensitive information securely. Navigation systems, algorithms are used for the shortest path calculation and route optimization. So, in conclusion of algorithms, summary, algorithms are essential for solving problems efficiently and effectively in computer science. They are also helpful in understanding different problem-solving techniques, and their complexities is key to designing and optimizing solutions. Designing optimized solutions. Final thought: mastering algorithms and problem-solving techniques opens the door to tackling complex challenges in software development, data science, and artificial intelligence. Next, we'll look at the basic programming concepts. So programming is all about giving instructions to a computer to solve problems. The three fundamental concepts in any programming languages are the variables, the data types, and the operators. Let's define these three. Variables. So a variable is a named location in memory used to store data that can be referenced and manipulated. So variables are essential for holding and managing information during program execution. Let's give an example in Python. So we have age is equal to 25. Age here is a variable storing a number 25. And there's some rules in regards to naming variables. So variable names must start with the letter A to Z, so, or an underscore, followed by letters, numbers, or underscores. They cannot be reserved. They cannot be a reserved keyword. For example, if, for, or while. So these words here are reserved in programming languages. So example of valid names are age, total, amount. You can see here the total is in lowercase, and then amount starts with uppercase, and then score, it's underscore, and then score. So example of invalid names is 1, 2, 3, ABC, or 4, because these are used in loops. 4 is, which we'll see later as we dive deeper. Then data types. Data types specify the kind of data a variable can store. The most common data types are integers, int. These are whole numbers. We have what we call float or floating point. These are decimal numbers. So any number that's a decimal is called a float. In string, these are text or characters, and then boolean, where it's a condition, so it can either be true or false. So an example in Python, we have age, like we said. So this is a variable age, but it has a data type of an integer, which is a whole number, 25. And then we have a variable height, but it's storing a data type of a float, 5.9. We have a variable name, it's storing a string, which is a text, Alice. Then is student, this is the variable, but it's a boolean, so it can either be true or false. As we continue looking at the common data types, so integers, whole numbers, can be positive or negative. And then the floats, these are decimal numbers, the strings, these are a sequence of characters. And the boolean, true or false values. So it can either be true or false. Then what are operators? Operators are symbols used to perform operations on variables and values. They allow you to manipulate data. The types of operators, we have arithmetic operators, comparison operators, and logical operators. For arithmetic operators, we have addition, like the plus sign, so it adds two operands. For example, 5 plus 3 is equal to 8. Subtraction subtracts the right operand from the left. Multiplication multiplies two So this is basically math, if you remember your math. A division and modulus, so divides two operands and returns the remainder. For example, 5, so we use the percentage mark, yeah, 2. So we have the comparison operators title. Comparison operators equal to, so this is how we do equals, so it's not singular, yeah. If you just use one, it won't work. So this returns true if both operands are equal. So for example, 5 is equal to 5. Then we have not equal to, this is how it is, this is the syntax for not equal to. So it's an exclamation mark and then the equal signs. So it returns true if operands are not equal. For example, 5 is not equal to 3. And then we have the greater than, returns true if the left operand is greater. For example, 5 is greater than 3. And the less than returns true if the left operand is less than the right operand. For example, 5 is less than 8. And then for logical operators, we have an operator called AND. Yeah. So it returns true if both conditions are true. For example, true and false equal to false, or returns true if at least one condition is true. For example, true or false. Then not reverses the result, returns true if the condition is false. For example, not true is equal to false. And then combining operators. So you can combine arithmetic, comparison, and logical operators to perform complex complex operations. For example, in Python, you have a variable x storing an integer 5, another variable y stores an integer 3. So the result, x is greater than y and x does not equal to 0. Print result, the output will be true. In conclusion, understanding variables, data types, and operators is essential to writing effective code. These concepts are the building blocks of any programming language. With practice, you'll be able to apply these concepts to solve real-world problems. Then we'll look at arrays and lists, structure, indexing, and simple operations. And arrays and lists are fundamental data structures in programming. Both are used to store collections of elements. They define structure, flexibility, and operation. So we'll be defining them hand in hand just to see the difference. So an array is a collection of elements, all of the same type, stored in contiguous memory locations. This is continuous. Yeah, contiguous. The key characteristics: the size is fixed, it has efficient indexing, memory is allocated sequentially. And then a list is an ordered collection of items which can be of different data types. So the difference here is that an array, the data types are the same, they can't be mixed. Then key characteristics of the list, the dynamic size, so it can grow or shrink. It may or may not be contiguous in memory, so it depends on implementation. And it has a more flexible than, it's more flexible than arrays. Then to define the structures. The structure of arrays, like we said, arrays have a fixed size, so once declared, the size of the array cannot be changed. The elements, all the elements are stored in contiguous memory locations. And then for indexing, the arrays use an index to access elements, so starting from 0 in most programming languages. So let's say if you want to get the first item in an array, the first one starts from 0, doesn't start from 1. Then the structure of lists, the size is dynamic, so the size of the list can change during program execution. The list elements may not be stored in contiguous memory locations. Then indexing, like arrays, lists often support indexing to access elements, though some lists, like linked lists, may not. Indexing in arrays, so accessing elements, use the index, accessing elements in arrays, use the index to access or modify elements. For example, we have an array 3, so this here accesses the 4th element, so indexing starts at 0. So since it starts at 0, that means it will be counting 0, 1, 2, 3, meaning number 3 is the 4th element. Indexing starts at 0 in most programming languages, Python, C, and then Java. So there's an example of an array here. We have an array and these are the elements 10, 20, 30, and 40. So array 2 here, if we want to access, that means it will return this value 3, because 2 is actually the 3rd, meaning this is 0, 0 is 10, 1 is 20, and then 2 is 30. So in lists, so accessing elements in lists, so similar to arrays, lists allow indexed access. In some languages, lists can be dynamic, so the indices may not directly reflect contiguous memory addresses. For example, in Python, we have a list called mylist, and 5, 10, 15, 20. So we'll say print mylist and then 2. The output is 15 again. Then insertion. Insertion in arrays, again it's a fixed size. So insertion requires creating a new array if the original array is full. So for example, inserting into the 2nd position, we have an original array here, 10, 20, 30. After insertion, 10, 20, 5, then 20, then 30. So we've added this in the 2nd position. So the operation complexity, insertions at the end of 1, and then insertions in the middle of n, and then the shifting elements. And then in lists, A list allow easy insertion at any position. An example, insert at the end, my list, append. So this is the method for inserting 25, and then insert at a specific index, my list, to insert 125. So we have a list here, and then the insert method, so it will insert 7 at index 1. So the result will be 5, and then 7, 10, 15. And then deletion or deleting. In the deleting in arrays, the deletion typically involves shifting elements after removing an item. For example, deleting from the second position, the original array will look like that, and then after deletion, And then in lists provide easy removal of elements with operations like .remove. I usually call these methods, but yeah, they're operations. .remove, and then .populate. So remove by value, my list .remove, and then you list the value, and then remove by index, my list .pop, and then put the index. And we know that this index here, 1, means it's the second item on the list. So here when you're removing by value, my list .remove, and you 10, so it removes 10, so it just becomes 5 and then 15. A few applications of arrays and lists. Arrays applied in storing fixed size locations like sensor readings, game boards. And then in lists, applications used in dynamic data handling, such as a collection of user inputs, dynamic queues, and stacks. Stacks and queues are fundamental data structures in computer science. These data structures play a crucial role in AI, especially in search algorithms. They help organize and manage data efficiently for problem solving. What is a stack and what is a queue? A stack is a linear data structure that follows the last in and first out principle. The key characteristic: elements are added and removed from the same end, called the top. These are some of the operations used in stacks. We have push, then insert, pop, remove, pick, and then the view top element. So push inserts, pop removes, and then pick views the top element. So we have an example of a stack here, 3 to 1. The top is number 3. And then define a queue. A queue is a linear data structure that follows the first in, first out principle. Elements are added at the rear and removed from the front. Few operations are in queue, this inserts, dequeue, this removes, and then pick views the front element. So we have a queue of 1, 2, 3. The front is 1 and the rear is 3. The role in AI, both stacks and queues are used in search algorithms to traverse and explore possible solutions. They help manage the order in which nodes or states are explored. They are critical for implementing algorithms like depth-first search and breadth-first search. So DFS and stack, or depth-first search and stacks. So DFS is a search algorithm that explores as far down a branch as possible before backtracking. The stack is used to store nodes, pushing nodes onto the stack as they are visited and popping them when backtracking. An example use case, searching for a path in a maze where we need to explore paths until we hit a dead end, then backtracking. Example of DFS traversal: start at node A, push A onto the stack, move to adjacent node B and then push B, and then continue until all paths are explored. Then the breadth-first search and queues. The BFS, or breadth-first search, is a search algorithm that explores all nodes at the present depth level before moving on to the next level. The queue is used to explore nodes level by level. An example use case, finding the shortest path in an unweighted graph. An example BFS traversal, start at node A and queue it, dequeue A, visit its neighbors and then enqueue them, and then continue until the target is found. The comparison between DFS and BFS in AI. So for DFS, the use cases, again, solving puzzles like the 8 puzzle, maze exploration, and problem solving where solutions are deep in the search space. One of the advantages is that there's less memory usage compared to BFS, and can find solutions that are far from the start point. The disadvantage: may get stuck in deep or infinite loops unless properly managed, and there's no guarantee of finding the shortest path. Then the BFS, the use case in comparison, it's for finding the shortest path in games, social network analysis, or shortest path problems. One advantage is it guarantees the shortest path in an unweighted graph. The disadvantage compared to DFS is that there's high memory usage, especially in large graphs. Case examples. Use case 1, solving the 8 puzzle with DFS. We have a problem. The 8 puzzle is a sliding puzzle where the goal is to arrange tiles in a specific order. Now using DFS, so DFS explores all possible moves, pushing new states onto the stack until it finds a solution. Example of DFS algorithm steps: start with the initial puzzle state, push all possible moves onto the stack, and then pop states and explore further until the solution is reached. And then use case 2, finding the shortest path in a graph with BFS. We have a problem where, given an unweighted graph, find the shortest path between two nodes. So while using BFS, the BFS explores each level distance from the starting node using a queue, ensuring the shortest path is found. The example steps is it starts at node A, enqueues it, dequeues A, and then enqueues all unvisited neighbors, and then it continues until the destination node is reached. Applications of stacks and queues in AI. For stacks, backtracking algorithms, solving puzzles, game trees, maze solving, memory management in recursive functions, function calls or function call stack. Then queues, scheduling problems, so CPU scheduling, task execution, level order traversal in AI, trees or graphs. A few challenges with stacks and queues. For stacks, it may result in deep recursion or infinite loops without careful management. It's limited by the last in, first out principle, which may not be ideal for all such strategies. And then for queues, it's memory heavy. For large graphs in BFS, due to storing all nodes at each level, and may not be efficient for very large datasets without optimization. And we're going to look at the introduction to time and space complexity. The overview: algorithms are the foundation of computer science. Evaluating their efficiency is crucial for performance and scalability. The big O notation is a way to measure the efficiency of algorithms in terms of time and space complexity. So what is time complexity? Time complexity is a measure of the amount of time an algorithm takes to complete as a function of the input size. Key points: it describes how the runtime of an algorithm increases with the size of the input, and then it helps determine the scalability of an algorithm. It is expressed using the big O notation. And space complexity, so it's defined as a measure of the amount of memory space an algorithm uses as a function of the input size. The key points: it describes how the memory usage grows as the input size increases. It's important for systems with limited memory resources. The big O notation overview. In definition, the big O notation provides an upper bound on the time or space complexity of an algorithm. Its purpose is to help us understand the worst case scenario for growth of an algorithm's time or space requirements as the input size increases. Then we have an example here. Common time complexities in the big O notation. We have O1. This is a constant time, so the algorithm takes the same amount of time regardless of the input size. For example, accessing an element in an array by index. Then we have O, the logarithm of n. So this is the logarithmic time. The algorithm reduces the size of the input by half with each step, for example in a binary search. Then O of n, this is the linear time. So the algorithm's runtime increases linearly with the input size, for example iterating over an array. Then we have O of n log n, this is the log linear time. It's common in efficient sorting algorithms like merge sort and quick sort. It's more efficient than
Maria had caught such a big fish.
O n squared for large inputs, which is the next one we're looking at. So O n to the squared O to the power of 2, this is the quadratic time. The algorithm's runtime grows quadratically with the input size. For example, nested loops, such as in bubble sort. Then O to the power of n, this is the exponential time. This is the algorithm's runtime doubles with each additional input element. For example, brute force solutions to certain combinatorial problems, like the traveling salesman problem. Some examples of time complexity. For the first one, we're using constant time. So the problem is accessing a specific element in an array. Reason, no matter the size of the array, accessing one element takes the same constant time. N of n, the problem, finding the maximum value in an unsorted list. So the reason is that the algorithm needs to check each element once, so the time increases linearly with input size. That's the logarithmic time, the linear time of n. Then O n squared, we have a problem where it's a bubble sort algorithm. So the reason why we'll use this time complexity is it has two nested loops. So for every element, it checks every other element. I hope you can see that. And then defining the space complexity with the big O notation. Example of one. So the problem here is a function that just returns the sum of two numbers. The reason is only a constant amount of space is used, regardless of the size of input. And then example 2 of n. The problem is creating a new array to store results from a loop. The space needed grows linearly with the input size. In some examples, we have an example problem of swapping two variables. The amount of space used doesn't depend on the input size. And then for the linear, storing all the elements of an array in a new list. That's the example. And the reason is the space usage increases linearly with the size of the input. So why is the big O important? For three reasons: efficiency, scalability, and comparison. In efficiency, big O helps you choose the most efficient algorithm based on time and space. For scalability, it allows you to predict how algorithm will perform with large inputs. For comparison, big O notation helps in comparing the efficiency of different algorithms. Sorting algorithms, we have double sort. This is the O n to the n squared. So this one is inefficient for large data sets due to quadratic time complexity. It's simple, but it's slow for big inputs. Then the merge sort, O n logarithm n, it's more efficient for larger data sets. So even though it uses extra space, it performs better as input size grows. In summary, for the big O notation, O1 is constant time or space, O logarithm n, logarithmic time or space, it's very efficient. O n is linear time or space, O n logarithm n, log linear time or space, commonly seen in efficient log algorithms. O n squared, quadratic time of space, slow for large inputs. O2 to the power of n, exponential time of space, infeasible for large inputs. So these are the best, worst, and average case scenarios. So the best case scenario is where the algorithm performs the least amount of work. For example, insertion sort. Best case, it's already sorted. The worst case scenario is where the algorithm performs the most work. For example, merge sort or quick sort, worst case scenario. The average case. So the expected performance considering typical inputs. Then look at optimizing algorithms. Number one, time complexity optimization. Use more efficient algorithms. For example, O n log of n, which is the log linear time complexity method here, instead of the O n to the power of 2, which is a quadratic time. Avoid unnecessary loops and redundant calculations. Then for space complexity optimization tips, you will minimize memory usage by reusing variables or using more memory efficient data structures. Real world examples. Let's say we're searching in a database. A binary search on a sorted list is O log n, which is much faster than a linear search. Example 2, let's say social media feeds. Implementing sorting algorithms and recommendation systems that need to handle large amounts of data efficiently. In conclusion, the three key takeaways. The big O notation is essential for understanding the efficiency of algorithms. Time and space complexities help evaluate and compare algorithms. Optimizing algorithms for both time and space is crucial for handling larger inputs effectively. and yeah, basics problem solving using algorithms. So this is introduction to algorithms and their problem solving techniques. So problem solving is a critical skill in computer or computer science or computing and programming. It involves identifying a problem, finding a solution, and then implementing it. And algorithms are the step-by-step procedures used to solve problems. Guess we'll define what an algorithm is again. An algorithm is a well-defined step-by-step procedure to solve a problem. It takes the input, processes it, and then produces an output. For example, a recipe is an algorithm for making a dish. The key characteristics of algorithms: definiteness. Each step must be precisely defined. Finiteness. The algorithm must end after a finite number of steps. Effectiveness. Each step must be basic enough to be performed. Input and output. The algorithm takes input and produces output. I feel like we're repeating some of these things. Anyway, it's important. So the problem solving steps using algorithms. Number one, it understands the problem. Understand the problem. So identify the inputs, outputs, and what needs to be done. Devise a plan. Choose an algorithmic approach. We looked at this earlier. For example, brute force, divide and conquer. Implement the solution. Write the code or follow the steps of the algorithm. Test and verify. Check if the solution works correctly with test cases, and then analyze, evaluate the efficiency and correctness of the solution. We'll look at a simple problem to solve here. Find the sum of all numbers in the list. The algorithm will initialize the sum, and then loop through each number in the list, add each number to the sum, and then return the sum. We have a code snippet here. It's an example in Python. Define sum of list, numbers. Total is equal to 0. So for number in numbers, total will be that. Then to return total. Okay, so it's been an hour. I guess we'll end today's lesson here and then proceed from here tomorrow. Otherwise, thank you for tuning in. And don't forget to subscribe to the channel, like the video, leave a comment, and check out the video description for all the necessary links that you'll need to follow up on this. Thank you for tuning in. Have a blessed day.